Hello and good day, geometry. We are starting our final unit of the year, and that is on circles. I've literally saved the best for last. And as it is with most units when we first start out, there's a lot of terminology stuff that we just have to get through. Some terminology, some theorems. Some of this, no doubt, you've heard before. But for the stuff that you haven't, all of them are wise owls, so they can all go on a help sheet. You can pick and choose what you need, but we're going to define it, as well as draw a picture of it so you know what it looks like. Let's see if we can fit all these on one, so I don't have to, that was too far. So I don't have to delete any as we go. Good. All right, so first up is a radius. This one you should definitely know. What is the radius of a circle? Yes? Okay, and so tell me more.
It's like, so the dot that ends the radius is the center of the circle.
Yes.
So the radius is the line that connects the edge of the circle to the center.
Okay, so it is a segment because it does have a beginning, it does have an end, and that's important because the fact that it's a segment means it's measurable, right? We can't measure a line, can't measure a ray, but we can measure a segment. So it's a segment that connects the center of a circle to the edge. A segment that connects the center of a circle to the edge. I feel weird using the word edge because the circle doesn't really have edges or sides, but maybe a point on the outside of the circle, but that's too many words, so we'll use edge. And what it looks like, the radius, if you got a circle here, from the center to the edge, that would be the radius. It's usually represented by the variable r for obvious reasons. You use it a lot in your area formulas, your surface area formulas, your volume formulas. Whenever you have a circle and a formula, you can pretty much guarantee that that radius is going to be a part of it. Pi also, but radius also. A chord might be new. Anyone know what a chord is in relation to circles? Okay, it is a segment, so again, we can measure this, a segment that connects 2 points on the edge of a circle. A segment that connects 2 points on the edge of a circle. So essentially, it's a segment going through the circle. That would be an example of a chord. It's got endpoints on the edge of the circle. Okay. The diameter, yes, Noah. Yes, and so the diameter is also a chord, right? It's a very special chord. The diameter is a chord that passes through the center of a circle, okay? And whenever you see a dot, that represents the circle's center. So even though it looks like I didn't quite hit the center there, since I've labeled it the center, you can safely not assume, you can conclude that is the center of a circle. And as I think it was Daniel said, the radius is half the measure of the diameter. The diameter is twice the measure of the radius. The diameter is a chord. Okay. Secant. Any idea what a secant is? Okay, a secant is a segment or ray or line. Remember my abbreviation for that is SRL, just because I don't want to write them all out. But a segment, ray, or line that passes through a circle. So it doesn't start at one edge and end on the other edge. It actually passes through it. And so an example of that would look like this. Maybe it passes through the center, maybe it doesn't. I'm not marking the center to show you that it doesn't have to pass through the center, but any segment, ray, or line that passes through the circle is referred to as a secant. Okay. Tangent. How annoying that they use a similar word for two completely different things. You've got tangent ratio in a triangle. You also have the tangent of a circle. A tangent is a segment, ray, or line that touches a circle at exactly one point. A segment, ray, or line that touches a circle at exactly one point. So, probably draw it out here so it looks a little bit more room to write it here. A tangent line is going to come down, just nick the outside there, and continue on its way. So it doesn't pass through the circle at all. Okay. In order for something to pass through the circle or go into the circle, it has to touch 2 points on the circle, except it has to come back out again. This one just touches it once. That is a tangent line. The point of tangency is the point where a tangent intersects the circle. The point where a tangent intersects the circle. So in our case, the point of tangency is going to be right here. Okay. Finally, common tangents would be a tangent, segment, ray, or line that is tangent to more than one circle. A tangent, segment, ray, or line that is tangent to more than one circle. An example of this might be, I also want to draw my tangent line first so I can accurately do it here. You got one circle up here, another circle down here. That'll be a common tangent. Don't quite connect, so I'll just make my point bigger. There you go. There you go. That's an example there. Whew. Questions on any of this? I said, it's a lot of vocab. You got some new words in there. Chord, secant, tangent, point of tangency, common tangents, definitely new. Sounds like radius, diameter. You know what those are. But we'll be using these phrases, using these words a lot in future objectives. So, questions so far? Okay. Two theorems involving tangents. Theorem 10.1. Okay. Basically, what this is saying is that that was a pretty good circle. A line that is tangent to a circle is perpendicular to the radius of the circle. Okay? A line that is tangent to a circle is perpendicular to the radius of the circle. In words, a tangent line is perpendicular to the radius. Okay, which means that there's the potential for what here? Some right triangle action going on. So all that stuff from the previous 2 units coming back again. Okay, Theorem 10.2 says that if you've got 2 tangents that intersect at the same point, those tangent lines or tangent segments from here to here and here to here are congruent. Okay? So tangents that intersect at the same point are congruent. I should say tangent segments because lines can't be congruent. Tangent segments that intersect at the same point are congruent. Okay? Questions on that? Does that make sense? Where have you seen kind of that diagram before? Anyone recognize it from science class, maybe? Pac-Man. Never had that said before, but I guess so. Sometimes this is used to show what happens in an eclipse, but maybe, yeah. Nick?
I said this is what I think those cubes look like. I said the first one looks like the person from the ancient Greece pushing that stone up.
Yes.
And the other one looks like some chopsticks holding some like sushi or something.
Oh, also good. See how much fun circles can be? And we're just getting started. Any other questions or comments? That was a good one. Okay, going on to the second page. Here's where we get to label and practice some of the things we talked about on the front side. It says here, use the diagram to identify the different parts: the diameter, the radius, the secant, tangent, chord, and point of tangency. I'm going to pause the video. Go ahead and work with your table mate and write in the different pieces there, and we'll talk about them shortly. Are we going? Okay, we're going. What did you put for the diameter of this circle? AB could be the diameter of the circle, and you really should have the segment marking above it. Without the segment marking, you're saying the measure of AB, but it is actually segment AB. Another option is segment BA, right? Segments can be interchangeable in how we write them. If you put C is the center of the circle, but it is just a point. Okay, the diameter goes from one point through the center to the other one. For a radius, you could have segment AC, you could have segment CA, you could have segment CB, or segment BC. Either of those would be fine. How about a secant? What'd you put for a secant? Yes. AE. AE works. Okay, because it does, A does go through the circle and does pass through point E. You could also have AG. Okay, because AG is the same line as AE is, so either one would be correct. You could have GA, you could have EA. Those reversed, not a problem there. Yes. Tangents. What's our tangents? Christopher? DE would be a tangent, and you could put that as a segment or a ray or a line. Actually, it doesn't make a difference. ED would also be fine there. If you put line DB to put the point of tangency, that would be fine, but the point of tangency is point B there. And then finally, the chord, you could put AG as a segment, GA as a segment, or you could write either of the ones you put up for the diameter, because the diameter is a chord. It's a very special type of chord. Questions on any of that? No? You're all circle experts now?
No.
Oh.
Guaranteed.
On our way there, though. Okay. The next section here talks about is DE tangent to circle C. You've seen me use this symbol in math packets before, but this symbol here is the symbol for a circle. Okay, it's just a circle with a dot in the center, so that refers to circle C. And the question is DE tangent to it, and how do we know? What must be true for a tangent line to exist? Look back at Theorem 10.1 if you have forgotten. What must be true? Gabby?
It only passes through the circle once.
Okay, so tangent only has passed through the circle once, which it does there at point D. What else must be true in order for a tangent to exist? Josh? It's perpendicular to the radius. So essentially what we're trying to prove here is that this angle is a right angle. Now, how might we go about proving that that is a right angle? Grayson? Pythagorean theorem, right? Were you making fun of me? Oh, that's not very nice. Pythagorean theorem, a squared plus b squared equals c squared, where c is the hypotenuse. So a squared, our radius is 3, plus b squared, our other leg, is 4. What's the length of our hypotenuse? CE. Nick?
5.
Why is it 5?
So 3 is the radius.
Yes, very good. Yeah, we're only given that 2 there, but because CE, goes from the center to the edge, this section of it is another radius, which makes the total length of CE 5. And you should recognize this hopefully as a Pythagorean triple. 3 squared plus 4 squared does indeed equal 5 squared. So yes, it is a tangent line, and we know that because the Pythagorean theorem works. The next one, you are told that ST is tangent to circle Q. Show how you can find the value of R. You're told that ST is tangent to circle Q, which means that this is a right triangle here. It has to be 1 because of theorem 10.1. How can we find the value of R? What do we have to set up here? Yeah.
Inverse, tangent, sine, cosine.
That gives us angles. We don't want angles. The value of R it's the value of the radius.
So Pythagorean theorem.
Pythagorean theorem. A squared plus B squared equals our hypotenuse C squared. So A squared is our radius. B squared, our other leg, is 24. And what represents our hypotenuse? Noah? 18 plus R, or how we're more accustomed to seeing it, R plus 18 squared. Oh, look, you get to foil crab claw or box. Who knew this would have come up in geometry, right? Yay! So we can rewrite this to be R squared plus 24 squared. What's R plus 18 factored out? Foil crab claw box. Who's got it? Foil crab claw box. R plus 18 squared. If this is confusing, just replace the R with an X, and it's should recognize that from PO45. Yeah. R squared plus what? Ooh, you're missing something. Remember, you can't just distribute that exponent in, right? You have to actually take R plus 18 times R plus 18. If you just distribute the exponent, then you miss that middle term. Josh? 24? Okay. Now this is kind of annoying, the fact that we have exponents involved here, but what's at least nice about the way this sets up now? What? The R squareds cancel out, right? We have 1R squared on the left, 1R squared on the right. We can just get rid of them. And so essentially, we're left with a two-step equation to solve here. 24 squared is something like 576. So 576 equals 36R plus 324. Subtract 324. Divide both sides by 36. And we get a radius value of 7. Questions on that process? I got 7. What other folks get?
7.
Oh. Subtract 324 from both sides and divide by 36. Okay. Christopher.
So why would you put the 36R in the right half of the equation?
Because this expression here is what we get from squaring R plus 18. This is what it looks like all written out in expanded form. But if you foil, crab claw, or box that, remember when you square a binomial, you're going to get a polynomial, which is what our last month of algebra has all been kind of going with. Okay. All right. Other questions? Last one on this page. I appreciate your willingness to plug on here. Show how you can find the value of x or values of x. What could x be? Noah? How do you get that? Oh, how do you know that they're equal? Theorem 10.2, yes. Since these two tangents come from a common point, they are congruent, meaning that x squared is equal to 9. So to solve this, you would root both sides, meaning that x is equal to 3 or negative 3. Okay? And in this case, x can actually be negative 3 because the length of that tangent isn't negative 3. We square that to get positive 9. So both answers should technically be included. Christopher?
So if you just wrote 3 for that would be wrong.
No, on the test, if there's something that does have two answers, if you write the other one also, I give you an extra credit point. So if, what? If I remember.
Is it still extra credit if you don't remember?
But it'll just, if I remember to remind you or not. That'll be the question. Yeah. We are. But hey, here's the good news. It's on circles. Yeah. Huh? Yeah. It's not due till next Monday, technically. In the plus side. You've made it this far, folks. We are almost there.
The home stretch?
The home stretch. Okay. It is a lot of writing. CO60 actually goes pretty quickly. Despite the writing. Because just like how segments have measures and angles have measures, circles have arcs, which have measures, right? We talk about a triangle or a quadrilateral. We've got 180 degrees in a triangle, 360 degrees in a quadrilateral. Each angle has a measure. How many degrees are in a circle? Any circle, no matter how big or how small, 360. And how we measure those degrees is by using arcs. So draw your best circle here. Ooh, that's not bad. That might be one for the scrapbook. Sure I do. All my best lessons, I take screenshots of this and put it in my scrapbook. Yeah. Wow, that was cold. Good one, but cold. Woo. Okay. And a central angle is an angle with its vertex at the center. That's why it's called a central angle of a circle. Those of you that came to the geometry placement test review session a couple weeks ago, you've already we talked about this, okay? But now we make it official. You should recognize some of these things we talked about then. So let's draw in a central angle. We're going to make our center of the circle there, and let's draw this out like that, okay? And here's point A, and here's point B. And here's the thing about a central angle. Here's the important part. Its measure is equal to the arc it creates. Okay? The measure of a central angle is equal to the measure of the arc it creates. I should put to the measure of the arc it creates. Use all the lines here. Measure of the arc it creates. Okay? And if you're asking yourself, well, what is an arc? What do you mean by that? This would be an arc. The distance around the outside of the circle from point A to point B would be arc AB. Arc AB. And we call it a minor arc because it's an arc with a measure less than 180 degrees. Okay? A minor arc is an arc with a measure less than 180 degrees. Okay? And so if this angle here was 145 degrees, then the measure of arc AB would be 145 degrees as well. Okay? And how you write that would be AB with a little arc over it there, little hat on top, equals 145. Okay? A major arc, I'll do this one in blue. A major arc is an arc with a measure greater than 180 degrees. And so this would be a major arc going from A all the way around to B. Right? Now, if I just ask you for the measure of arc AB, to know what you mean, the minor arc or the major arc. Well, the difference is that a major arc has to have a third point. So you would have to add a third point somewhere on the arc. And then to notate this, we would say arc ACB. So a major arc will always have 3 letters to show you that you're kind of going a long way around. A minor arc only uses 2 because it's the most direct arc path from A to B. Okay? So arc ACB, what would the measure of arc ACB be? If the minor arc there is 145, what is the measure of arc ACB?
215.
And how'd you get that?
Well, the area around the circle is 360.
Right. Just like 180 is associated with any triangle, all 3 angles must add up to 180 degrees. All arc measures must add up to 360 degrees. So if we know the minor arc is 145, the major arc, since there are only 2 of them, the major arc would have to be 215. All right? Semicircle, which you know what that is, right? Semicircle?
Half circle.
Half circle. Semicircle is an arc with a measure equal to 180 degrees. So just like in a right triangle, or in a triangle, we have acute, less than 90, obtuse, greater than 90, right triangle, equal to 90. Same kind of thing here. Minor arc, less than 180, major arc, greater than 180, semicircle, equals 180. And so what must be present for a semicircle to exist? You can't have a semicircle without this specific thing, the diameter. Okay? The diameter is what separates a circle in 2 halves. That's what gets you the 180 degree arc measure. Okay? The arc addition postulate, just like the segment addition postulate, just like the angle addition postulate, an arc measure is equal to the sum of its parts. And I'll draw one more thing in my circle up there to illustrate this point. An arc measure is equal to the sum of its parts. So arc AB here, if I were to add another section here, and we'll call this point D, okay? If I tell you that this is 30 degrees here, What's the measure of arc AD? If that angle D, well, to the center, and B is 30 degrees, what's the measure of arc AD? Christopher? 115. Okay. The 30 degrees here plus the 115 of, I should label this, AED has to equal the 145. So same kind of thing that we've talked about before with angles and segments. Whew! How we feel? Oh, come on. Anyone need his notes? Okay. The work down below says identify the arc as a minor arc, major arc, or semicircle, then find the measure of the arc. So we'll just kind of start here. TQ, okay? I wouldn't recommend drawing all the arcs in. It's going to get kind of messy for you, but I've got the luxury of being able to erase this, so I'll do it up here. But arc TQ, is that a minor arc, major arc, or semicircle? Christopher? Minor arc. And you know that because there's only 2 letters, right? And it's also clearly less than 180 degrees. It's less than half of a circle. And so what is the measure of arc TQ? 120, because it's equal to the measure of its central angle. Okay? Let's take one that's a little more challenging here. Arc QT, or QRT, which means it's from Q through R all the way up to T. We could have also named this QST, right? From point Q all the way through point S and up to T. We have that third letter just to show that it is what type of arc? Major arc, right? It's more than 180. It's got 3 letters in it. I didn't write minor on the first one. I'll write major here. And what's the value of that? How do you get that?
Because you take 120 and it's like on the bottom there. No. Oh wait.
Yeah, it's not quite a vertical angle here. Okay. The temptation is to make this a 120, but then if you think that this arc measure is 260, 260 plus the 120 we know is more than 360. So it's very slight, but SQ is not a diameter there. So how would you figure that out?
You take 360 minus 80 minus 120 minus 60.
Okay, there are only 4 angles here, right? We know 3 of them, 120, 80, and 60. So 360 minus 120 is 240, 240 minus 80 is 160, and 160 minus 60 is 100. So what's the measure of arc QRT? 240. Okay. You could have also found that just by subtracting 120 from 360, because if arc TQ is the other arc that we didn't use here, we already found that one, just take that away and you're left with the rest of it. So this is what your homework is going to be on this. Do you want homework on the other page?
No.
I mean, it'll help you prepare for the test. All right. Just this page then, CO60 for homework. Okay. Questions, comments, concerns, complaints, comments, congratulations, and criticisms? All right, that's IMath.